Welcome back. What we worked out in the previous segment was the form of the stiffness matrix for a general element. We'll proceed now with getting together the other parts of our matrix vector version of the finite dimensional weak form. And the first thing we have to do is carry out a similar integration for the forcing function term, that is the distributed body force term. Right? So let's start with that. Okay. So we will next consider the following term. Integral over omega e WH f a dx. All right, no gradients in here, so this actually becomes a somewhat simpler integral to calculate. It's integral over omega e. For WH, we have sum over a NA CA E, and we'll put parentheses around here to remind ourselves that this is what WH is represented as. We have f a dx. Now, because we know that NA ultimately is represented in terms of xi, that is the coordinate in the bi-unit parent domain, and because we know that we have available to us this map, right, for the geometry, the isoparametric map. What this tells us is that we can very well write this as an integral now by changing variables as an integral over omega xi sum over a c a e, and the reason we can do that is what? The reason we can pull CAE out of the integral is because, of course, it's just a degree of freedom that is used to build our representation of the weighting function. It does not depend upon C, right, or does not depend upon position. So we were able to pull it out just as we've been doing all along. All right, and remember that this sum runs A going from 1 to 3, right, for 3 nodes in the element. All right, we have CAE NA F A. Now, the integral over dx can now be written as dx dxc dxc. And of course, we remember from before something we calculated a couple of units ago, dx dxc is he over 2. All right, we're going to go ahead and build this integral, and in order to build it, let us just in order to be able to fix ideas and get something that we can compute, let us consider the situation where f and a are uniform, right? They're uniform over omega e, right, over the element of interest. What this allows us to do is to pull f and a as well out of the integral, right? And he is, of course, the element width, which is independent of c, right? So what that tells us is that what we're trying to compute from up here, right, I've represented it here in dots with ellipses. This is sum a equals 1 to 3 C A E times F A H E over 2 integral minus 1 to 1 N A dxc. Right? Now, just as we did before in the case of linear basis functions, and just as we did in the previous segment in order to compute the left-hand side integral, right? We go now to matrix vector notation. All right. So what we're trying to compute on the left-hand side, right, the integral that comes from the top of the slide, is now represented as C1e, C2e, C3e, using vector notation for representing our degrees of freedom of the weighting function over the element, times f a h e over 2. Now we get a vector here, right, and this is integral, the first component here is integral minus 1 to 1 n1, right. N1, however, we already know is 1/2 c times c minus 1 dc. N2, the integral from N2 is integral minus 1 to 1, or the integral from the integral for component 2 is integral minus 1 to 1 of N2, which is 1 minus c square dc, right? And the third component is integral minus 1 to 1 1/2 c times c plus 1 dc. All right. Okay, we'll go ahead now and compute those integrals. They are relatively straightforward to compute. Let's do that. We get our c vector for the element. We have f a h e over 2, because f and a we're assuming are uniform. And for our integrals, we get here first, we get 1/2 of c cube over 3, limits minus 1 to 1. For the second one, we get c minus c cube over 3 minus 1 to 1. And for the third, we get 1/2 c cube over 3, also minus 1 to 1. Right? When we compute these out, we see that we are left with C1e, C2e, C3e, f a h e over 2, and here we get 1 over 3, 4 over 3, 1 over 3. Right. Okay? So this is our general representation of the contribution from the right-hand side forcing function term for a general element. Okay? What we're going to do now is go to assembly, right? So, assembly of global matrix vector equations. All right. Now, it's worthwhile, just in order to position ourselves, to recall that what we're attempting to do here is actually carry out an integral over the entire domain, right, over our entire 1D domain. And we've used this partition into elements to write that as a sum over element integrals. Of that term, that element integral, equal to the sum over elements of that element integral plus a term which arises from the fact that we have a, what kind of a boundary value problem do we have? We have a Dirichlet-Neumann boundary value problem, right? So we have WHL times T, which is attraction, times A. Okay, so this is our finite dimensional weak form expressed as a sum over element integrals. And we've just, over the last previous segment and over the first few minutes of this segment, learned how to compute this integral in the last segment and that integral in this segment for general elements. Okay? Okay. Now, in order to carry out the assembly, we just need to recall something. Okay? We need to recall that for the Dirichlet-Neumann problem, right? Because we know that UH at 0 equals some given value which actually is equal to 0 in this case, right? What that implies for us is that WH at 0 is also equal to 0, right? Because we have a Dirichlet boundary condition at x equals 0. We also have a homogeneous Dirichlet condition on the weighting function. Of course, in this case, it turns out that our Dirichlet condition on the left-hand side at x equals 0 is itself homogeneous, meaning we're saying that the trial solution there has to be 0. Okay? Even if it were something other than 0, if it were non-zero, we would still have a homogeneous Dirichlet condition on the weighting function, right? And that's just the nature in which we've built our weighting function. Okay, the weighting function space, in fact. All right, so what does this mean? What this implies is that for element 1, okay, because WH at 0 is equal to 0, we construct WHE equals 1 as sum A not starting with 1 but starting with 2 to number of nodes in the element, which is 3. Okay, so we have this NaCAE. Okay, and in fact, going from local to global numbering of degrees of freedom, we will get here here's what we get, okay? Here's what we get. Because of the fact that we can go from local to global numbering of nodes, here's what we get. When we write out our matrices, right, matrices and vectors coming from our weak form, here's what we will get. We will use the fact that this thing can be written explicitly as N2 times C 2E plus N3 C 2E plus 1 for E equals 1. Okay, we're going to use this. Where do we use it? Here's what we get, right? Our global equations for the matrix vector weak form. Okay, they take on the following form. For element E equals 1, we have something a little special, right? We have here C2E, okay, C 2e plus 1. Okay, this is for e equals 1. Okay. In fact, let me do this. Let me explicitly use the fact that e equals 1 here. When I do that, C2e becomes C2 and C2e plus 1 becomes C3. Okay. We have 2e a over h1. Okay. We're assuming here, of course, that E and A are uniform or not only over each element, but also between elements, right? Effectively over the entire domain. There is nothing preventing us from developing the more complicated formulation where E and A are allowed to vary with position. Okay, all right. Now, what we get for the matrix contribution here is a matrix that is not square, but has only 2 rows. Okay. And in fact, that matrix has the form minus 4 over 3, 8 over 3, minus 4 over 3, 1 over 6, minus 4 over 3, 7 over 6. Okay. Multiplying it here, however, is the full D vector for that element. Okay, that would be D1 in terms of global node numbers, D2 and D3. Okay, that's all for element 1. Okay, and note that I've called that H1 for E equals 1. This plus now sum E equals 2 to number of elements. Here things look the same. 2e minus 1, the same as for a general element. C2e minus 1, C2e, C2e plus 1. 2e a over he. Our matrix which we developed in the previous segment, which is 7 over 6 minus 4 over 3, 1 over 6, 8 over 3, minus 4 over 3, 7 over 6, completing by symmetry. Right, all of this multiplying here, d 2e minus 1, d2e, d2e plus 1, right? Global numbering of degrees of freedom in nodes. Okay, so those terms together, that's this one for the first element and this for a generic other element, give us our left-hand side. This is now equal to, okay, the right-hand side. Again, the same thing happens with the forcing function contribution. Okay, so we get for the C vector for the forcing function contribution, again we get C2, C3. Okay, the contribution here is F A H1 over 2, and it multiplies a vector which is just 4 over 3 and 1 over 3. Okay. The first element, the first entry, the first component from the general form of the vector that arises from the forcing function is absent, because in element 1 we start with that global degree of freedom, because the weighting function satisfies the homogeneous Dirichlet boundary condition. All right, we have this plus sum over E equals 2 to number of elements. C2e minus 1, C2e, C2e plus 1, FA HE over 2. Now we get the full form of this vector, 1 over 3, 4 over 3, 1 over 3. In addition, let's never forget the Neumann boundary term, right, which is WH at L, but that is simply C2 NEL plus 1 times TA. Okay, that's it. That's really our weak form written out fully in matrix vector notation.